morning to everyone. My name is Nashiru Billa, and I'm in the University of Nottingham, Malaysia campus. I'll be sharing with you some research that we are working on currently, which is as shown on the title up there. I know it's a bit of a mouthful, but it's an ongoing work, well, I'll just show you some of the results that we've had over the next couple of minutes, perhaps. Now, there's been a lot of talk over the past couple of days. Yesterday and just next door, we have some presentations going on diabetes. We know how serious this is a problem to us. It has a very wide-ranging economic impact on us. And it's all because of our lifestyle changes. We've become much lazier over the course of years, and as a result of that, this is going to get worse. There will be more people who suffer from diabetes. There are many forms of diabetes, and I'm sure every one of you here probably have some idea of what it is and how it manifests itself. So I'm not going into the details of that, but just suffice to say that type 1 diabetes is probably the worst of the two because it requires us to take externally administered insulin, and that means that the individual has to inject himself or herself repeatedly. And that can lead to very uncomfortable situations. It can even be life-threatening in some cases. So there has been some interest over the past couple of years in trying to solve this problem by coming up with delivery systems which can deal with this issue. And that is what my research is, one of my research team focuses on. So I'll just share with you some of the things that we have had over the couple of years. Now, for such a delivery system to deal with this issue of the body not able to release enough insulin to deal with the fluctuations in glucose concentration, the delivery system should ideally act much like the pancreas. In other words, it should be able to sense the presence of glucose and release insulin accordingly. And this mechanism should be like a feedback. So it should just be like the pancreas, ideally. So that's the concept that a responsive or glucose responsive delivery system should work on. There are many examples of sensors or delivery systems being studied currently, if you check on the literature. And we have decided to focus on boronic acid, which has been studied quite extensively as well. Actually, in the past, boronic acid was used as a sensor to test the presence of glucose. And we thought that we could use this to produce a delivery system by the same mechanism, that is, the delivery system being able to sense the presence of glucose, and then if the delivery system has within it insulin, then the insulin can be released as a result. Boronic acid is relatively safe. When used internally, it's broken down into systems which are quite degradable, boric acid in the body, so that's not a problem. So we refer to boronic acid essentially as any boronic acid containing an aryl or an alkyl group attached to the boronic acid unit, which is shown up there. And this boronic acid has got a very strong affinity for diols. So any diols present in the media will react reversibly with the boronic acid and produce either a trigonal or tetrahedral conformation. And these two different conformations very much depends on the pH of the medium, so whether it's acidic or alkaline. And we have different rate constants that govern this reaction. In the case of the trigonal conformation, usually it's faster and the most preferred. But when the solution is alkaline, then we do have the tetragonal, which is the alternative, second alternative for reaction. So we thought that, well, if we produce a delivery system which can sense glucose and be able to release insulin as a result of that sensing, then that delivery system perhaps might expand. And through that expansion, there will be release of insulin accordingly. And so we propose this schematic for the trigger. And there are many examples of the models that are based on different types of delivery systems. For example, the lectin carnitine A can be linked to a polymer, which then interacts with glucose. When it interacts with glucose, it has a stronger affinity, and therefore it's able to release insulin as a result. There are many other examples out there. So in this case, as I said, we are focusing our attention on boronic acid. So this unit here is showing that the different keys over here, which you can have a look up. This is the glucose, and that is chitosan. And we decided to use chitosan in our formulation because it's a very well-studied polymer. It's biocompatible, and it's easy to fabricate as well. And this here is insulin, and here is the glucose sensor, which is boronic acid, as I said earlier on. So the first thing obviously requires us to synthesize the conjugate. And the synthesis is by a process known as N-alkylation, where we have the chitosan made to react under alkaline conditions with boronic acid, under acidic condition with boronic acid. And this interaction is actually preceded by a nucleophilic attack, as shown by the arrow over here. And this leads to the formation of an intermediate, which is very unstable, and therefore arranges itself or rearranges itself to this from this unstable to a shift base, and the shift base is then reduced using the reducing agent, sodium borohydride, and finally we have the chitosan conjugates formed. So that was the reaction carried out, and once the conjugates were formed, we tried to purify the conjugates by washing with methanol as well as ethanol. And then we freeze-dried the conjugates until further use. The conjugates were tested to be sure that the boronic acid had been tagged. So we did a few basic tests, such as FTIR analysis, and that proved that there was actually a boronic acid or a phenyl moiety attached, which was absent in the chitosan. And furthermore, we could see that there was an increase in this phenyl group as we increase the amount of boronic acid during the synthesis. So we find over here that F6, for example, has a higher intensity of phenyl group, which shows therefore that the boronic acid had been tagged. We tested the conjugates to their propensity to interact with glucose, and this graph is showing the amount of glucose absorbed on the y-axis, and on the x-axis shows the different formulations, and you can see that there is an increase in amount of glucose absorbed up to a point, that is as F3, and then it sort of falls off afterwards. And the reason why this has happened, we believe, is because of the nature of the conjugates. When you look at the SEM images of the conjugates, you can find that they look somewhat spongy and porous from F1 through to F3. And as we further increase the amount of boronic acid from F4 to F5 to F6, the conjugates appear to be a bit more crystalline. And if they are crystalline, then it's difficult for the boronic acid to interact with glucose favorably. We believe this is the reason why this has happened at the conjugate stage. Now, for a delivery system to act in vivo, within the body, it should essentially be able to act at the right pH. So we tried to see how much of the glucose was absorbed onto the conjugates as a function of pH. And you can see that at pH 7.5, we had the highest amount of glucose absorbed, and then it sort of falls off here. Various reasons why this could be the case. It has to do probably with the pKa of glucose, among other things. But suffice to say that it's quite favorable, the fact that we have quite a significant amount of absorption at pH 7.5, which is around the physiological pH. So that was quite rewarding. We also did a time of flight secondary ion mass spectroscopy of the boron fragment, and you can see very clearly here that chitosan has no entity. Okay. So this is the time of flight scan of the conjugates, and you can see very clearly that we do have a high amount of boron in the conjugates as we increase the amount of boronic acid entities from F1 right up to F5. So we went then further to synthesize, to formulate the insulin-loaded nanoparticles, and we use a very simple and well-established method based on ionic gelation. So we use the conjugates was dissolved in an acidic medium, and was cross-linked with tripolyphosphate, which is a polyanion, and the magnetic stirring. The nanoparticles form spontaneously, so it's a very simple and straightforward method. This is showing the scan of the nanoparticles before and after images. Well, the first panel on the left side is the insulin-free nanoparticles, and the one on the right is the insulin-loaded nanoparticles. It's hard to tell the difference because the magnifications are quite different, but it appears to be that the insulin-free nanoparticles are somewhat rough in surface topography compared to the ones containing insulin. A few characterization of the nanoparticles, including the zeta average, which is just an indication of the size, as well as the surface charge or zeta potential. You can see that as the amount of boronic acid was increasing in the formulation, we have a reduction in the size, roughly, as well as a reduction in the charge. And all of these are quite understandable because the boronic acid interacts with the amine group of chitosan, and as a result, that tends to reduce the charge on the nanoparticles, since the charge is actually due to the amine group. And so we find there's a reduction in the charge as we increase the amount of boronic acid. Now, this is called the nanoparticle tracking analysis. It's a technique that is used to track individual nanoparticles as a function of time, and it's quite useful. This is not working now, is it? I want to be able to point this off. Okay, so if we just focus on, I know the image looks a bit fuzzy, but if we just focus on one of the graph at a time, we start with the blue graph, which is the profile showing the concentration of particles as a function of time. You can see that most of the particles are essentially skewed to the left. Most of them are small in size, and this is when the nanoparticles are exposed to a low glucose concentration, which is 1 milligram per ml. So we find that most of the particles are skewed to the right over here. And when we increase the amount of glucose from 1 milligram per ml to 2.5 milligram per ml, that is this graph over here, you find there's a slight increase in size of the particles. From the blue one, there's a slight increase over here, okay? So it shows that the particle size is increasing as we expose the nanoparticles to glucose. And then when we increase it further to 5 milligram per ml, that's the green curve, you find that most of the particles are skewed to the right over here, to the left. And finally, when we raise the concentration to 10 milligram per ml, we find that most of the particles are right over there, right? So there's a clear indication that the nanoparticles swell when they are exposed to glucose concentration. When the amount of glucose concentration is increased, we tend to have an increase in size, which tends to support our earlier model that this is likely to be the case. However, when we monitored the amount of glucose release, it wasn't as expected.
Right, 2 minutes remaining, please.
Pardon?
2 minutes remaining.
Okay. The amount of glucose release was kind of not as expected. So we just focus on what happens. We compared the amount of insulin release, as well as the amount of insulin release when the nanoparticles were exposed to glucose and when they were exposed to fructose. And you could see That in the case of the when 1 milligram per when the glucose concentration was 1 milligram per ml, that's the curve we get over there. There wasn't that much change in the amount of insulin release as a function of time. But when the concentration is raised to 3 milligram per ml, as well as 5 milligram per ml, we find that there is a rise and a fall. This rise and fall is actually indicating that there is some kind of holding together of the nanoparticles because of the interaction between glucose and the boronic acid. It tends to hold and sort of zip the nanoparticles together and therefore prevents further release of insulin. This case is much more severe. In the case of fructose, you find that generally the amount of insulin release is lower at all the concentrations tested compared to the ones in the case of glucose. So I'll just rush over this because of time constraint. This is showing the scanning electron microscopic images of the nanoparticles before exposure, and this is the nanoparticle. Right, I'll just end here then, just straight to the conclusions. What we can see is that when we compare the glucose and fructose interaction, we find that the fructose appears to interact much more with the nanoparticles, and when it does so, it holds the nanoparticles together much more firmly, and when this happens, it means that there's less insulin release. And we're hoping, I believe, or maybe when the nanoparticles are given in vivo, this might be a reason for retaining the nanoparticle size required, as well as maintaining the release of insulin. So this is an ongoing work, and well, we hope that after some time we'll be able to have much more details on the mechanism of action and mechanism of release. So yeah, I'll end here.
Thank you so much for this nice presentation. Questions at the